Hi guys, welcome back. In this video, I want to solve an example of hydraulic systems. And I want to show you guys how we can use the equation for the tank for this example. So the way that we model these systems is extremely similar to electrical systems, and we take a four-step approach. In step one, we will go after the elements in the system. So list the elements. Okay. And for this one, we again go after inertia, stiffness, friction, and our sources. And we comment on the number of ODs. Okay. So by looking at this system, I noticed that inertia in hydraulic systems is the fluid inertance. And like we mentioned in the lecture, unless we are told to include inertance, okay, we can neglect this one. The next one is a stiffness. And we mentioned that the stiffness in the hydraulic systems is either the tank or the reservoir. And then we have a friction, yes? And we somehow lump the effect of all those friction in one friction element, which is the valve. And at last, we need to include the sources in the system. If you look at this system, you see that I have two sources from the environment. The first one is the input flow, which is Qn. And the second one is the pressure of the atmosphere. Okay, so I would include Qn and the P atmosphere. The last thing that you need to comment is the number of ODs. If you guys look at the system, you see that in this system, you have only one energy storing element, and that is the tank, which stores the energy as a potential energy. Yes. So you're going to end up with only one OD. Okay. Now that the ODs, the number of ODs is done, okay, and then you have a clear understanding of the elements in the system, let's go to step 2 and define the dynamic variables in your system. So if you remember, dynamic variables were in electrical systems were either the voltage across the capacitors or currents through the inductors. Yes, guys? So voltage for you guys in electrical systems was an effort, yes? And flow or the current was a flow. Yes? Okay. So what is effort in hydraulic systems? Well, in fact, it's going to be pressure. And what is the equivalent of capacitor in hydraulic systems? It's going to be the tank. Yes. Similarly, here you had the currents in the inductors. Now you're going to have the volumetric flow rate that passes through the inductance. Yes. So these two things are going to be your dynamic variables in the hydraulic systems. With this in mind, you notice that since I am neglecting the inductance in my problem, and I'm only considering the capacitance, which is the tank, then the pressure in the tank, which I showed with P, is going to be my only dynamic variable. Okay? So with this in mind, I'm going to go to step 3, which is basically writing down the ODE for that energy storing element. For energy storing element. Yes. For this problem, I have only one energy storing element, and that's the tank. I'm going to write down the ODE for that one. Okay. So if you remember, the conservation of mass, when you assume that the density is constant, okay, which is the case in hydrostatic pressure, it's going to reduce to this equation. Cp dot equals to Qn minus Q out. If you have several Qn or several Q out, you need to sum them up here. Okay. For my problem, I noticed that I have only one Qn and then one Q that goes out of this guy. Okay. And I'm going to show it with QC. Yes. Okay. So in my problem, okay, I would have just one of these guys. So I don't need to have summation here. Okay. So at this point, what I'm going to do is, in fact, I can keep that Q as Q out, because the current that passes, the volumetric flow rate that passes through the valve is the one that pours into the atmosphere. Okay, so I'm just going to keep it as Q out. Okay. At this point, what I'm going to do is I'm going to change my pen. Okay, and I would label these terms as good and not good. Okay, and if you remember from the electrical systems, your good terms were either your dynamic variables or your sources, your inputs. Yes. And whatever that's not your dynamic variable, that's not your input, it's not a good term, you have to rewrite there. Okay? So let's go and comment on P dot. Do you guys think that P dot is a good term or not a good term? Okay. So if you look at the system, you see that P dot is your dynamic variable, so it's a good term. Well, P is your dynamic variable, P dot is a derivative of that dynamic variable. Then I would go to Qn. Do you think that Qn is a good term or not a good term? Well, in fact, if you look at this, Qn is one of your inputs, so it's a good term. And at last, I'm going to go to Q out. You see that Q out is not your dynamic variable, it's not your input, it's not a good term. Which means that your job, my job, is rewriting Q out, which is not a good term, in terms of my good terms in step 4. So I would go to step 4 of this problem, and I would rewrite the not good terms in terms of my good terms. Okay. And what we're going to use here in this one is we are going to use the equation for the valve. Okay. So from the valve equation, depending on whether you assume that the flow across the valve is laminar or turbulent. Okay. If you guys remember, we had delta P, or pressure before the valve, and pressure after the valve. Okay. As pressure before, okay, minus pressure after the valve equals to either RL Q that passes through that valve, or if that's a turbulent, it's going to be RT or turbulent multiplied by Q squared. For this problem, let's assume, for the sake of simplicity, let's assume that the flow across the valve is laminar. Okay. Now we need to figure out what's going to be the pressure before the valve, what's going to be the pressure after the valve, and what's going to be the volumetric flow rate that passes through the valve. Okay, so notice that here the pressure before the valve is in fact the pressure at the bottom of the tank. Okay, and this is your dynamic variable. the pressure after the valve, since it pours into the atmosphere. Okay, you can assume that this pressure is actually pressure atmosphere. Okay, and the volumetric flow rate that passes through the valve is in fact what it pours to the environment. Okay, so rewriting this equation, before pressure, for the pressure before the valve, I'm just going to use P. For the pressure after the valve, I'm going to use P atmosphere. Okay, so it's going to be my P atmosphere. Okay, and like I said, I assume that it's a turbulent, it's a laminar flow. Okay, and for the Q, it's going to be Q out. Okay, now if you solve this equation for Q out, you see that your Q out would be P minus P atmosphere over RL. Yes. Now, let's look at the terms in this equation. P, do you guys think that it's a good term or not a good term? Well, it's my dynamic variable, so it's a good term. P atmosphere, do you think that it's a good term or not a good term? Well, okay, I think that it's a good term because it's my source. Yes? And RL is a constant number. I do not care about RL. Yes? So at this point, I was able to rewrite Q out in terms of my good terms. Yes? Okay. So let's call this equation as equation 1, and let's call this equation as equation smiley. Substituting 1 in equation smiley will get you, so let's say that Cp dot equals to Qn minus Q out. Instead of Q out, I'm going to put it as P minus P atmosphere over RL. Yes? Okay. Now, just to get rid of the RL in the denominator here, I'm going to multiply both sides of this equation by RL. Yes? So if you multiply both sides of this equation by RL, you will end up with RL C P dot equals to RL Qn minus P atmosphere. Yes? Okay. Now, keep the inputs on one side, bring all the dynamic terms to one side, okay, and check for the signs. If your signs match, then you're good to go. Yes? So this is going to be RL C P dot plus P equals to RL Qn plus P atmosphere. Okay. Now, look at this. I have on the left-hand side, I have one family, and that's family of P. Within that family, I have two members, P and P dot. And the sign for both of them is positive, so I do not have any sign mismatches. On the right-hand side, I have all the inputs. Okay, so this is one valid model for this tank. Yes? So let's call this equation as equation 2. So for my fundamental assumption here for deriving this equation was laminar flow. Yes. So here I assume that, let's say, valve assumption. Okay. My assumption here was that the flow across the valve is basically laminar. What happens if I change this assumption? If I assume that the flow across this valve is in fact turbulent? Yes. So in the second part of this question, what I'm going to do is I'm going to change my assumption. Okay. And my assumption in this part is turbulent flow across the valve. Okay. And if I assume that I have turbulent flow across this valve, then my equation for the valve is going to change. Okay, and that's the only part that's going to change. Like step 1 and 2 and 3 are going to be exactly the same, since I'm not changing any element in the system, and I'm not changing any dynamic variable, I'm not changing any ODE. Okay, and because fundamentally I'm not changing anything in the system. My only thing is my view towards the valve is right now as a laminar, as a turbulent flow instead of the laminar. Okay, so if you assume that the flow across the valve is in fact turbulent, then you have the pressure before the valve just like before, and the pressure after the valve just like before equals to right now RT Q out squared. Okay, now this is a nonlinear equation. This is not linear equation anymore. Yes? Okay, this squared guy here is a nonlinear term. So regardless, what we're gonna do is we're gonna solve this one for Q out, okay, and then we put it back into equation smiley. Yes, so solving for Q out, you notice that your Q out would be P minus P atmosphere over R turbulent, and you're gonna take the square root of this guy. Okay, and with this, okay, we're gonna, let's call this equation as equation, I think 3. Yes, and substituting equation 3 in equation smiley, you will get the model for a turbulent flow. Guys, note that I forgot to mention that here in equation 3, you have everything in terms of your good terms. P is a good term, P atmosphere is a good term, they're all good, okay, and R turbulent is a constant number, okay, so it doesn't affect anything. So, dynamically. So, if you go ahead and substitute equation 3, in equation smiley, you end up with what? You end up with Cp dot equals to Qn minus square root of P minus P atmosphere over R turbulent. Okay, and for this problem you can get rid of the square root, okay, and bring it to the other side, okay, and keep all the inputs on one side, all the dynamic variables or variables on one side, okay. However, since it's a nonlinear equation, okay, I'm just going to keep it as it is. So I'm going to bring only the square root to the other side, and I'm going to flip the sign, okay. So this is going to be Cp dot plus the square root of P minus P atmosphere over R turbulent equals to Qn. Okay, and this is the dynamics of the system when you are assuming that the flow across the valve is turbulent. Good? Okay. So the last thing that we want to do, okay, is working with equation 3 and equation 4 and equation 2, okay, and reformulating these dynamics in terms of the fluid height. Okay, so if you remember, okay, so this is the part 2 of this problem. Okay, if you remember, basically you want to formulate everything. Formulate equation 2 and equation 4 in terms of the fluid height. Okay, so if you remember, for hydrostatic pressure, we had P equals to rho GH, yes, plus P atmosphere. Okay, so You notice that in this problem, P atmosphere is a constant number, okay? And for hydrostatic pressure, you guys notice that you can assume that the density is constant, okay? And also, the gravitational acceleration is going to be constant in a tank, okay? So if you assume these numbers to be constant, and this is the expression for P, okay, then your P dot, if you take the time derivative of this guy, your P dot will reduce to rho G H dot. Yes. Why? Because rho and G are constant. They act like a multiplier. Okay. And H is the only term that has derivatives. And P atmosphere is also constant. The time derivative of constant is always 0. Yes. Okay. So let's call this equation as equation 5. Okay. And this equation as equation 6. Yes. So what we're going to do is we're going to go ahead and substitute in equation 2 and equation 4 instead of P dot from equation 6 and instead of P from equation 5. Okay. So if you want to formulate the laminar flow, okay, assuming laminar flow, across the valve, okay, what we can do is basically we can copy and paste equation 2. Okay, let me just copy and paste equation 2 here. Okay, and so your equation 2 was CRL, okay, and P dot plus P equals to QN multiplied by RL plus P atmosphere. Yes. Okay. So let's go ahead and substitute for P dot and P. Yes. So if you go ahead and substitute for P dot, so it's going to be CRL. Instead of P dot, you just put it as rho G H dot. Okay. And instead of P, you put it as rho G H dot plus P atmosphere. This is going to be equal to RL QN plus P atmosphere. Okay. And let's simplify this equation a little bit. So P atmosphere with P atmosphere will go away. Okay. And you will end up with this dynamics as C or L rho G H dot plus rho G. I made a mistake here. This should be rho G, not rho G H dot. Okay. Plus rho G H equals to RL QN. Yes. Okay. Again, guys, to just make sure that you didn't make any mistakes, check for the signs. Yes. So you have one family on the left hand side, and that's the family of H. Within that family, you have two members, H and H dot. And you see that all these numbers are constant, okay, that are multiplied by each other, and they're all positive. Okay. So you do not have any sign mismatches within the family members. You can simply go ahead and box this equation. This is the equation of the dynamics of your system when you want to model everything in terms of the height. And you assume that the flow across the valve is laminar. Okay. Now, what if you change your assumption? What if you change the flow to turbulent? Okay. So assuming flow turbulent across the valve, so if you assume that the flow is actually turbulent across the valve, the only thing that you need to do is you need to go back to equation 4. Okay. And in this equation, you are going to basically substitute P dot and P. Okay. So let me just copy equation 4. So I'm going to copy this equation. Okay, and so by substituting 5 and 6 in equation 4, okay, you will end up with this. Okay, let me just rewrite equation 4 here. Okay, that's your equation 4. Okay, and in this equation, what we're gonna do is we're gonna simply, instead of P dot, we're gonna put it as rho GH dot. Instead of P here, we're gonna put it as rho GH plus P atmosphere. Okay, so it's gonna be C rho GH dot plus the square root of rho GH plus P atmosphere minus P atmosphere divided by RT. It's going to be Qn. Yes, guys? Okay. Now look at this. P atmosphere with P atmosphere will go away. Okay. You will end up with C rho GH dot plus the square root of rho GH over RT. Yes, equals to Qn. Okay. And this is your dynamics. Okay, if you want to model everything in terms of the height of the fluid in the tank, okay, and also assuming that the flow across the valve is turbulent, not laminar. Okay, and you might ask yourself that, well, okay, why should I go after different models for this system? For instance, why should I go after the height of the tank here instead of the pressure? It really depends on the availability of your sensors. Yes. So if you can measure the height, okay, which is probably the cheapest way, okay, or if you have a pressure sensor and you can measure the pressure, okay. So this is basically two different views towards the model. Which one do you want to use to model the system, pressure or the height? Okay. Thank you.